Hello everyone, I'm Michael from SDU Center for EnergyInformatics at the University of Southern Denmark. Today, my presentation is about time series called the Inference for analyzing the energy efficiency for industrial processes with a Foundry case study. This is the agenda for today's presentation. It starts with the motivation and the background of the research. Nowadays, improving energy efficiency and reducing CO2 emission is more and more important in the world. For example, the International Energy Agency set the goal of net zero emissions by 2050, and the United Nations COP28 conference set the goals of doubling energy efficiency and tripling renewables capacity by 2030. Therefore, it is very important for the industrial sectors to improving energy efficiency and reducing CO2 emissions in their processes. Here is some data to support the view. In the energy and the users, the industry ranks the first for the energy consumption, and it is also the largest CO2 emission contributors. More detailed, among the industrial energy end users, the iron and steel sector contributes to the second largest energy consumption and the largest CO2 emissions. Therefore, it is essential to provide decision support for improving energy efficiency in the iron and steel industry. In this study, we selected the foundry industry as a case study, and especially analyzing the melting cycles in the furnaces in the foundry industry. To provide the decision support for improving energy efficiency in this sector, these two research questions should be answered. The first one is, what are energy efficient and energy inefficient operations? And the second is, what causes energy efficient and the energy inefficient operations? To answer these two research questions, some data analysis methods should be employed. To answer the first question, the clustering algorithm can be employed to classify the energy consumption patterns into different groups. And to answer the second question, the causal inference methods can be employed to identify the cause and effect relationships among the variables in the energy-related industrial process variables. The first question has been answered in my previous publication. So some results of the clustering analysis will be directly used in this study. And this paper mainly focuses on the causal influence in the industrial processes with the Foundry application. Next, I will introduce the methods and algorithms employed in this study. First of all, I will introduce the data analytics pipeline of the study. The industrial process operations will firstly be segmented into different slices. For example, in the foundry industry, the melting cycles will be identified and segmented, and then the segmented melting cycles will be classified into different groups, such as the energy efficiency groups and energy inefficiency groups through the clustering algorithms. The first two steps has been analyzed in my previous publication, and this paper will focus on the third and the fourth steps. After we have the clustering results, the causal inference algorithm will be employed for each cluster to produce the causal structure for the data in different clusters. And then the post hoc analysis will be conducted to compare the different causal structures in the different clusters, including within cluster analysis and cross-cluster comparisons. For the time series causal inference, the PCMCI plus algorithms is used in this study. We choose the PCMCI related algorithm is because the PCMCI algorithm itself was developed especially to analyze the complex and nonlinear real-world time series data. The PCMCI algorithm quantifies the causal strength of large-scale nonlinear time series datasets based on conditional independent tests, and its extension, PCMCI Plus, includes the discovery of instantaneous relationships to enhance the reliability of causal detection. In the PCMCI Plus algorithm, some CI tests are developed. The shown 4 CCI tests are important and useful to analyze the real-world continuous variables. The fourth CMI method is especially useful for multivariate and continuous variables. But in the tests, we find that the first 3 methods is also useful to identify some correct cause-effect relationships that the CMI method cannot find. Therefore, in this study, we combined these 4 CI tests through the shown intersection and the union operations, so that to reduce the false discovery rate and improving the accuracy of the causal inference. We have employed 3 different synthetic data sets to test the methods, and the results shows that the developed hybrid methods can further improve the accuracy compared to just use one CI test. Next, I will introduce the case study in this paper. First of all, I will introduce the processes of the working flow in the Foundry. Firstly, the metals and alloys are gathered and then they are delivered to the induction furnaces for melting process. Then the molten alloys will be transferred into the holding furnaces, and based on the requirements of the orders, the required alloys will be collected for casting. The melting process in the entire industry processes are chosen at a case study because it accounts for about 55% of the electricity consumptions among all the stages. Here is the description of the data sets used in this study. There are 12 different time series variables, and the sampling period of the sensors are 10 seconds. Especially in this study, the subset of each cluster should be selected for causal inference because the entire time series dataset is over 1 year. And if we run the causal inference algorithm directly for each cluster, the run time is very long, and it's impossible to get the causal structure very quick. So it is necessary to select the representative data sets for each cluster for the high efficient data analysis. Then I will show the results for the inference for each cluster. In the clustering algorithms, 7 clusters are identified. Some of them are energy efficient groups, and some of them are inefficient groups. Here is the results, the causal structure of each cluster. The nodes with the numbers represent the variables, and the numbers shows the as shown in the numbers in the previous slides to describe the data set. And the arrows and the lines show the direction from cause to effect. The values near the linkage are the time lag, because the sampling period of the dataset is 10 seconds. So here 1 means 10 seconds, and for example 3 means 30 seconds. The colors and the width of the links shown in the legends represents the causal strength of the cause effect relationships. For example, if its color is red and the width is large, it shows the causality effect is strong. And then we analyze the occurrence frequency of the different causal pairs. For example, the causal effect pairs, variable 5 effect variable 11 occurs 6 times among the 7 clusters. Here are some key findings of the causal inference analysis. Firstly, we can find the relationship of voltage influences the cooling water temperature appears in 6 clusters, and the time delay is minimum 30 seconds. Secondly, some very important causal relationships for directly regarding the energy efficiency are found. For example, the specific energy are influenced by the total energy and the furnace temperature. It's very interesting, and based on the domain knowledge, it's correct, because specific energy means the energy consumption per unit per wage. So it is influenced by the total energy consumption, by the temperature, and the weight is meaningful. And then we also find some cluster-specific causal behaviors. Here we show 3 representative clusters, including the largest group, the high energy efficiency group, and the low energy efficiency group. Finally, I will discuss and conclude the contributions and the limitations of this study. For the contributions, first of all, the causal inference algorithm directly analyzes the causes and effects of the energy efficiency related variables. It identifies the true causal drivers beyond the correlation analysis. Secondly, the causal inference for different clusters identifies some interesting and various causal structures. In each cluster, some common and some different causal links are identified, and we can compare the different causal links among the clusters to conclude and generate the valuable insights to make recommendations for the industrial participants. Finally, for the methodological contribution, the combination of clustering and causal discovery and analysis is fundamental and novel methods that can be used to analyze the energy efficiency not only in the foundry industry but also in other sectors. This study still have some limitations. First of all, for the domain and the data perspective, only one furnace in one foundry is analyzed here. In the future study, more furnaces and more foundries or some other industrial sectors can be analyzed use the same clustering and causal inference methods. Next, in the current stage, we only analyze the observational causality, but it has not been verified by the real-world scenarios. In the future study, we can do the do some experiments in the real-world scenarios, or do some tests in the digital twins by setting some specific scenarios to validate and verify the causal structures. This is my presentation. Thank you.